Hey everyone, and welcome. I'm Saurabh Kaushik, and today we are going to break down a super interesting topic that's literally everywhere, from your morning chai to the most advanced chemistry labs. All right, let's jump right in.
Have you ever actually thought about this? You're making chai, you add a spoonful of sugar, and suddenly the way it boils just changes. Or, hey, why do people add salt to water when they're cooking pasta? Well, the secret to all these kitchen mysteries is hiding in one simple, really elegant law.
Now, before we can get to the main law, we absolutely have to meet the hero of our story today, and that is vapor pressure. Trust me, once you get this one concept, everything else is just going to click right into place.
So what even is vapor pressure? I mean, the technical definition is right there on the screen, but what does that actually mean in a way that makes sense? Well, let's make it way simpler.
I want you to imagine a party, a really big party. The molecules in a liquid are all the guests. Now, the easier it is for these guests to escape the party and head for the door, the higher the pressure builds up right at that exit. And that, in a nutshell, is vapor pressure. So, the party is going great, right? The molecule guests are leaving freely, everything's cool. And then, Raoult's law makes its grand entrance, and it's brought along some uninvited guests, the party poopers. And believe me, they are about to change everything.
Look, at first, when it was just the pure solvent, the party was lively. Molecules were escaping easily. But then you added a non-volatile solute. Think of sugar. These sugar molecules, they're the party poopers. They don't want to leave. They just hang around the surface, standing right by the exit and blocking the way. So now the original solvent molecules find it way harder to get out. And because of this, fewer molecules can escape, and the pressure at the exit gate, our vapor pressure, it goes down.
And this whole phenomenon was perfectly captured in a law by the brilliant François-Marie Raoult. He figured out that the partial vapor pressure of any component in a solution is directly proportional to its mole fraction, which is just a fancy way of saying it depends on how much of it is there. So the really crucial point is that we can actually predict how much that pressure is going to drop.
All right, let's take a quick peek at the math that's going on behind this party. And don't worry, I promise it's actually really straightforward. We're basically just going to do a head count of the guests.
So this formula here describes what's known as the relative lowering of vapor pressure. All it's saying is that this value, the amount the pressure drops, is exactly equal to the mole fraction of the solute, our X solute. So in our party terms, it just means the pressure drop depends entirely on the ratio of party poopers to the original guests. Simple as that.
And this right here, this is a huge deal. This reveals a key concept of something called colligative properties. The law doesn't care if you added sugar or salt or some other crazy molecule. All it cares about is how many particles you added. It's all about the numbers.
But does every party follow the rules? Does every solution obey Raoult's law? Absolutely not. Some solutions behave like perfect, ideal students, but others are total rebels. Let's find out what makes them so different.
So, ideal solutions are the ones that follow Raoult's law perfectly. In these, the attraction between the original guests and the attraction between the old guests and the new ones, it's all pretty much the same. Think benzene and toluene. But then you have the non-ideal solutions, and this is where the party gets dramatic. Here, the forces of attraction are all unequal, and the solution just deviates from the law.
The first type of rebel is one that shows positive deviation. This happens when the new guests and the old guests, well, they just don't really like each other. The attraction between them is weaker than the attraction they have for their own kind. So what happens? The molecules are basically thinking, I got to get out of here, and they escape more easily. This causes the vapor pressure to be higher than what Raoult's law would predict.
And the second case is the complete opposite, negative deviation. This is when the new and old guests become best friends. The attraction between them is way stronger than their original bonds. Now they don't want to leave the party at all. This makes it harder for molecules to escape, and the vapor pressure ends up being even lower than expected.
So why are we even talking about all this? Why is this one law so important? Well, it's because its effects, its afterparty, show up everywhere, in our daily lives and all across the world of science.
You see, Raoult's law is the absolute foundation of all colligative properties. This whole idea of lowering vapor pressure, it's directly responsible for the elevation of boiling point, the depression of freezing point, and even osmotic pressure. All of these huge concepts are direct consequences of Raoult's law. It's all connected.
And now, it's time for a little pro tip from me, Saurabh. You want to know something really cool?
Raoult's law is actually a special case of another really important gas law called Henry's law. When you take Henry's law and apply it to a volatile component in a solution, it actually simplifies down and becomes Raoult's law. Pretty interesting, isn't it?
So let's come all the way back to our pasta question. When you add salt to the water, you're adding party poopers, right? So the vapor pressure of the water goes down. This means, to get that water to actually boil, you have to heat it to a higher temperature to build that pressure back up. And there you have it. The boiling point elevates.
And now I have a little challenge for you. Sometime today, go into your kitchen and just look around. See if you can spot Raoult's law in action. Think about where you can see its effects, maybe from making sweet drinks to defrosting food in the sink.
And that is all for today. I really hope you'll now look at all kinds of solutions with a fresh, new perspective. Keep exploring and never stop learning. This is Saurabh Kaushik, signing off.